Hello everyone. In this time, we group 3 will presenting about chapter 10, regression analysis, estimating relationship. Regression analysis is the study of relationship between variables. It is one of the most useful tools for a business analyst because it applies to, to so many situations. The branch of statistics that studies such relationships is called regression analysis. Regression analysis is one of the most pervasive of all statistical methods in the business world. There are several ways to categorize regression analysis. One categorization is based on the overall purpose of analysis. Regression can be used to understand how the world operates, and it can be used for prediction. A second categorization of regression analysis is based on type of data being analyzed. There are two basic types: cross-section data and time series data. Cross-sectional data are usually data gathered from approximately the same period of time from a population. In contrast, time series data involve one or more variables that are observed at several, usually equally spaced points in time. The dependent variable is the single variable being explained by regression. The explanatory variables are used to explain the dependent variable. Regression can be used to analyze cross-sectional data or time series data. A simple regression analysis includes a single explanatory variable, whereas multiple regression can include any number of explanatory variables. Scatter plots, graphing relationship. A good way to begin any regression analysis is to draw one or more scatter plots. Regression and causation. A successful regression analysis does not necessarily that, uh, that the X as cause Y to very uncertain way. In this one possibility, but there are two other. First, even if a regression of Y versus X is promising, it could very easily be that Y is causing X. That is, the causally could go the opposite direction. Second, and more common, the called the other variables that are causing both Y and the X to vary. This is precisely the role of scatter plots, to provide a visual representation of relationship or lack of relationship between variables. Scatter plots graphing relationship, linear versus non-linear. Scatterplots are extremely useful for detecting behavior that might not be obvious otherwise. We illustrate some of these in the next few subsections. First, the typical relationship you hope to see: straight line or linear relationship. Outlier. Scatterplots are especially useful for identifying outlier observation that lie outside of the typical pattern of point. An outlier is an observation that falls outside of general pattern of the rest of the observation. Unique variance. Occasionally, there is a clear relationship between two variables, but the variance of the dependent variable depends on the value of the explanatory variable. No relationship. A scatter plot can provide one other useful piece of information, can indicate that there is no relationship between of a pair of variables, at least none worth pursuing. This is usually the case when the scatter plot appears as a simplest form of point. Correlation, indicator of linear relationship. Correlation are numerical summary measures that indicate the strength of linear relationship between pairs of variables. A correlation between a pair of variables is a single number that summarizes for the information in a scatter plot. A correlation can be very useful, but it has an important limitation. It measures the strength of linear relationship only. Scatter plots and correlation are very useful for indicating linear relationship and the strength of this relationship, but they don't actually quantify the relationship. Remember, the simple linear regression does not mean easy, it means only that there is a single explanatory variable. Simple linear regression least square estimation. A fit value is the predicted value of the dependent variable. Critically, it is the height of the line above a given explanatory value. The corresponding residual is different between the actual and fit value of the dependent variable. Their formula for fundamental equal for regression, equation for slope in the simple linear regression, and equation for intercept in simple linear regression. Standard error of estimate. The magnitude of the residual provides a good indication of how useful the regression line is for predicting y values from x values. However, because there are numerous residuals, it is useful to summarize them with a single numerical measure. This measure called the standard error of estimate and denote CA. The S is essentially the standard deviation of the residual. This is formula for standard error of estimate. Simple linear regression, the percentage of variation explained R squared. R squared is the percentage of variation of the dependent variable explained by the regression. R squared measures the goodness of a linear fit. The better the linear fit is, the closer R squared is to 1. In simple linear regression, R squared is the square of the correlation between the dependent variable and the explanatory variable. Formula of R1.
Multiple regression. Multiple regression is an extension of simple linear regression. It is used when we want to predict the value of a variable based on the value of two or more other variables. The variable we want to predict is called the independent variable, or sometimes the outcome target or criterion variable. When you include several explanatory variables in the regression equation, you move into the realm of multiple regression. Some of the concepts from simple regression carry over naturally to multiple regression, but some change considerably. The following list provides a starting point that we expand on through this section. Interpretation of regression coefficient. The sign of a regression coefficient tells you whether there is a positive or negative correlation between each independent variable, the dependent variable. A positive coefficient indicates that as the value of the independent variable increases, the mean of the dependent variable also tends to increase. Interpretation of standard error of estimate and R-square. The standard error of the regression provides the absolute measure of the typical distance that the data points fall from the regression line. As is in the units of the dependent variable, R-square provides the relative measure of the percentage of the dependent variable variance that the model explains, standard deviation of residuals. So the interpretation of these quantities is almost exactly the same as in simple regression. The standard error of estimate is essentially the standard deviation of residuals. Modeling possibilities. Once you move from simple to multiple regression, the floodgates open. All types of explanatory variable are potential candidates for inclusion in the regression equation. In this section, we examine several new types of explanatory variables. These include dummy variables, interaction variables, and nonlinear variables transformation. Dummy variables. Some potential explanatory variables are categorical and cannot be measured on a quantitative scale. However, these categorical variables are often related to the dependent variable. So you need a way include them in a regression equation. Interaction variable. Consider the following regression equation for a dependent variable y versus a numerical variable x and a dummy variable t. If the estimate equation is from the form generic equation with no interaction, so then as in the previous section, this equation can be written as two separate equations. Yeah, and interaction variables is the product of two explanatory variables. You can include such a variable in regression equation if you believe the effect of one explanatory variable on y depends on the value of another explanatory variable. Nonlinear transformation. A nonlinear transformation changes or increase or decreases linear relationship between variables and thus change the correlation between variables. So for example of nonlinear transformation of variable x, we'll be taking the square root x or the reciprocal of x. The general linear regression equation have the form the predict y and you can see on the side. So the purpose of this is usually to strengthen out the point in a scatter plot. If several different transformations strengthen out the data equally well, the one that is easiest to interpret is preferred. Validation on the fit. The fit from a regression analysis is often overly optimistic. When you use the least square procedure on a given set of data, all of the idiosyncrasies of the particular data set are exploited to obtain the best possible fit. One way to see whether this procedure will be successful is to split the original data set into subsets. One subset for estimation and one subset for validation. A regression equation is estimated from the first subset. So finally, these predicate values are compared to the known value of the dependent variable in the second subset. If the agreement is good, there is reason to believe that the regression equation will predict well for new data. This procedure is called validating the fit. Conclusion. In this chapter, we have illustrated how to fit an equation to a set of points and how to interpret the resulting equation. We have also discussed two measures, standard error and R square. R square and standard error estimates that indicate the goodness of the regression equation, although the general technique is called linear regression. It can be used to estimate nonlinear relationships through suitable transformation of variables. That's all for my group. If you have any question, just drop on the description below. Thank you.